Good afternoon, students. So, this is class 14 of classical thermodynamics, and in this class, we'll see about chemical equilibrium, the effect of temperature and pressure on chemical equilibrium, as well as Van Hoff reaction isochore and isotherm. Consider a chemical reaction AA plus BB giving LL plus MM. Okay. So, for this chemical reaction, the free energy change delta G can be represented as G of products minus G of reactants. Okay. So, what is G of products? G of products will be equal to free energy of L plus free energy of M. Okay. So, in terms of chemical potential, we can write it as L into mu L plus M into mu M. Okay, since chemical potential are extensive properties, we have to multiply it with the number of moles of each component, and delta G, G of reactants will be equal to A into mu of A plus B into mu of B, so that delta G will be equal to L into mu L plus M into mu M minus A into mu A plus B into mu B. Okay, but we know that mu I, chemical potential for a component I, can be written as mu I0 plus RT ln AI, where AI is the activity of that component. Okay, since we are considering real systems, we have to consider activity instead of fugacity or pressure. So, substituting this, delta G will be equal to L into mu L0 plus RT ln AL plus M into mu M0 plus RT ln AM minus A into mu 0 A plus RT ln AA minus B into mu 0 B plus RT ln A of B. Okay. Now let's club together the mu 0 terms, that is chemical potential in the standard terms. So we have L into mu L0 plus M into mu 0 M minus A into mu 0 A minus, that can be taken outside, plus B into mu 0 B. Okay, so what is left is plus RT ln AL raised to L. Here we have L RT ln A raised AL. That can be written as RT ln AL raised to L plus RT ln AM raised to M minus RT ln AA raised to A minus RT ln AB raised to B. Here, take a look at this term. What does that mean? That is mu 0 of products minus mu 0 of reactants. What is that? That is delta G0. Therefore, we can write delta G is equal to delta G0 plus, what do we have here? RT ln AL. RT we can take outside, plus RT ln RT into ln, what do we have here? ln AL raised to L plus ln AM raised to M. That is ln AL raised to L into AM raised to M minus ln AA raised to A minus ln AB raised to B. So that can be written as AL raised to L into AM raised to M, AM raised to M minus ln AA raised to A into AB raised to B. What do we have here? This can be equated to delta G0 plus RT ln AL raised to L into AM raised to M divided by AA raised to A into AB raised to B. Now we have obtained the free energy change for the reaction AA plus BB giving LL plus MM. But at equilibrium, when the reaction has reached equilibrium, what happens? Delta G is equal to 0. At equilibrium, delta G is equal to 0. Then this equation can be written as delta G0 is equal to minus RT ln AL raised to L AM raised to M divided by AA raised to A into AB raised to B. Okay, where here we can substitute AL raised to L into AM raised to M divided by AA raised to A into AB raised to B as equal to Ka, where Ka is known as the thermodynamic equilibrium constant. This is thermodynamic equilibrium constant. Where Ka is in terms of activity of the reactants and products. This equation can be represented as delta G0 is equal to minus RT ln Ka. Okay, now we have obtained an equation for the free energy change in the standard state in terms of thermodynamic equilibrium constant. Okay, we know that activity A can be represented in terms of either partial pressure. We can denote activity in terms of partial pressures. In that case, AI is equal to gamma I into Pi. If we are representing activity in terms of molality, we can write AI is equal to gamma I into M. If we are representing it in terms of molarity, we can represent it as gamma I into capital M. Or if we are representing it in terms of mole fraction, gamma I into X. Okay, but so when we are representing Ka in terms of partial pressures, Ka can be represented as K of P, and when we are representing it Ka in terms of when we are representing activity in terms of molality, we can represent it as Ka into M, and when we are representing activity in terms of molarity, we will represent it as Kc. Rather than capital M, we will write it as Ka into C, and when we are representing activity in terms of mole fraction, we can write it as Ka of X. Thus, we see that there are 4 types of thermodynamic equilibrium constants depending on the units in which activity is expressed. Now, we have the equation delta G is equal to delta G0 plus RT ln AL raised to L into AM raised to M by AA raised to A into AB raised to B. Okay. So, from this equation, we obtained an equation for delta G0 by putting delta G is equal to 0 at equilibrium. Okay. So, let's put it here as E. This is at equilibrium. Okay, and at equilibrium we have activity as equal to Ka. Ka, thermodynamic equilibrium constant, is the ratio of activities of the products divided by ratio of activities of the reactants at equilibrium. Okay, so we have a term here, Al raised to L, Al raised to L into Am raised to M divided by Aa raised to A into Ab raised to B. Let it be equal to Q, which is known as the reaction coefficient. Reaction quotient. This is the reaction quotient. So, let's rewrite equation 1 by including Q and K delta G0. Okay. So, what do we have? Delta G is equal to, what are we doing? We are rewriting 1 by substituting delta G0 and Q. This is minus RT ln Ka plus RT ln Q. Okay. This equation, delta G is equal to minus RT ln Ka plus RT ln Q, is known as the Van Hoff reaction isotherm. This is Van Hoff reaction isotherm. Okay, so we have 4 types of equations: Van Hoff equation, Van Hoff reaction isotherm, and Van Hoff reaction isotherm. Of this equation is known as delta G is equal to minus RT ln Ka plus RT ln Q is known as Van Hoff reaction isotherm because this is applicable at constant temperatures. Okay, Ka is a function of temperature, and this equation is applicable at constant temperature, and hence this is called Van Hoff reaction isotherm. Okay, so this can be rewritten as delta G is equal to RT ln Q by K. This can be rearranged as RT ln Q minus RT ln K. Therefore, delta G is equal to RT ln Q by K. Okay. So, what happens if Q is greater than K? If Q is greater than Ka, then delta G will be positive. In such a case, what will happen? If Q is greater than Ka, delta G is positive and the reaction will not be spontaneous. What if Q is less than Ka? If Q is less than Ka, delta G will be negative, and in such a case, the reaction will proceed spontaneously and will reach equilibrium. At equilibrium, Q will be equal to Ka. Okay, this equation, this is the significance of Van Hoff reaction isotherm. Now let's see the other types of equilibrium constants. This is Ka, thermodynamic equilibrium constant. Q is reaction quotient. Now we'll see other types of equilibrium constant. Equilibrium constant in terms of pressure, in terms of concentration, and in terms of mole fraction.